Alright, finally our last review section, 2.5, is logarithmic functions. These are very, very closely related to exponential functions in the following way. In fact, I can give you a little bit more insight in just a moment as to how they're related. But here's our definition for starters. And, well, here's a logarithmic function. Y equals log to the base a of x. Right, so x is the variable. It's log to the base a of x. Right? So log to the base a is doing something to x. It's only defined for positive values of x, so x has to be bigger than 0. And once again, the a here, this is usually called our base of the logarithmic function. Our a here, just like exponential functions, has to be bigger than 0 and not equal to 1. And what does it mean? What is this number, log to the base a of x? Well, it means that a to the y is equal to x. You can think of this as being equivalent to definitions. You can always rewrite this expression. If you have y equals log to the base a of x, you can rearrange this in your mind to mean a to the y is equal to x. What does that mean? Well, think about this as sort of a number in its own right, because that's what it is, right? You plug in a value for x and it is a number in its own right, so log to the base a of whatever value x is. It's a number in its own right. It's equal to y. And this means that it is the number, so that when you raise a to that number, it equals x. So log to the base a of x is the number that when you raise a to that number, you get x, which is precisely what this says here. So a to the log to the base a of x is just x. And this is kind of cool, right? Think about this. Think about this. If I have a plus 3, and then I subtract 3, I've done nothing, right? I just get a back. So in some sense, addition and subtraction, they undo each other, right? They're inverse processes, they're inverse operators is the word mathematicians usually use. So addition and subtraction are inverses of each other. What if I did like a times 3, and then divided by 3? Well, once again, I get a back. Right, so multiplication and division are inverse processes. They undo each other. What this says is that if you take log to the base a of x, and then you exponentiate a, you get x back. Right? So taking a log of something and then exponentiating, they undo each other. So this is what a log really is as a function. It's the inverse operation of exponentiation. It undoes exponentiation. It's the complete opposite of it. In the same way that addition and subtraction are opposites, and multiplication and division are opposites. Alright, so some really quick examples here. Log to the base 3 of 9. What does that equal? Well, it equals the exponent that I have to raise 3 to make 3 to that power equal to 9. Right? So 3 to the what equals 9? 3 squared, obviously, right? Well, that's what this value is equal to, so that equals 2. How about this one? Log to the base 5 of 1 over 25. What's that equal to? Well, once again, this is asking 5 to the something equals 1 over 25. Well, what's 1 over 25? Another way I could write this is as 1 over 5 squared, right? Or 5 to the minus 2. So I'm looking for minus 2 here. So log to the base 5 of 1 over 25 is actually equal to minus 2. And last but not least, how about this one? Log to the base e of 1. What's that equal to, right? What power should I put up here to make e to that exponent equal to 1? Well, anything to the power 0 equals 1. Since e to the 0 equals 1, log to the base e of 1 is equal to 0. It's that exponent. Full disclosure, when I'm trying to compute values like this isn't actually how I proceed in my mind. I'm going to give you some properties that make computing expressions like this, so they're what they equal, a little bit easier. It's the way I usually think about it. But before we get to all those properties, once again, like I said in the last section, when I worked with functions, right, exponential functions, I like to have in my mind a picture of what the graph looks like, right? Just some general shape of the graph. So now that we've introduced logarithmic functions, I should draw the graph for you. So let's say this is y to the log, or sorry, y equals log to the base a of x, where a is bigger than 1. Alright, and I won't even do the case where, remember, it's allowed to be anything bigger than 0, just not equal to 1, so we could also do a between 0 and 1. We could look at that case. But it's so rarely used, bases between 0 and 1 are so rarely used, that this is really the log picture you should have in your mind. And it's not defined for x equals 0, right? It's only defined for positive values of x. So what does it do? Well, how about I start at the intercept? It intersects the x-axis right here at 1, 0. As x gets bigger and bigger, this function blows up, it gets large, but it gets large very, 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 very slowly. So eventually this gets bigger and bigger and bigger and bigger, as big as you want, but it does it very slowly, right? And in this direction, it gets super large negative and never crossing the y-axis. Alright, so this is the graph. And I'll show you something interesting about this graph, is that if I pretend this dotted line is y equals x, then this graph of y equals log to the base a of x is in fact just a reflection. It's a reflection. There's a 0, 1. It's a reflection of y equals a to the x, where we're looking at the a bigger than 1 case. All right, this is the exponential graph. The log graph is actually a reflection through y equals x of the exponential graph. So interesting relationship there, and it's precisely because, once again, these are inverse operations. They undo each other. That's why this is happening. So, there are many very important properties of logarithms that you should be very comfortable with working with, right? You have to know how to do log algebra to do anything with logs at all. So here's all of the properties. Log to the base a of x times y. So I'm taking log of a product. Turns out what you can do is you can write this as a sum of logs. So if I have log to the base a of x times y, I can write that as log to the base a of x plus log to the base a of y. So logs of products can be broken into sums of logs, really nice property. And similarly, logs of quotients, x over y, can be written as a difference of logs. The numerator is the positive term, log to the base a of x, minus the denominator, log to the base a of y. And this property actually follows immediately from this one if I combine it with property 3, which is log to the base a of x to the, we'll say r. Okay, so I'm taking log of x to some exponent r. And what you can do with this is this r can actually come outside. And I can bring this exponent outside as a constant multiple. So it's r times log to the base a of x. And these three properties are the three huge ones, right? You should absolutely know these inside and out to be able to work algebraically with log functions. But I'll give you a few more, right? There's a few more really important ones. Log to the base a of a. What does this equal? Again, it's worth just committing to memory instead of having to think about this every time. But what does it mean? It's the number that you raise a to make a equal to that, or a raised to that number equal to a. So it should be a to the 1 equals a. So it's just equal to 1. Log to the base a of 1. What power do you raise a to make it equal to 1? 0. So this equals 0. Commit that out of memory. And here's the two big properties that show that logarithms and exponents really undo each other. Alright, so we already had one. It was log a to to the log to the base a of r. Remember what this number is. This number is the exponent that you raise a to make a to that exponent equal to r. So this is r. Right, this shows if you take r, take the log of it to the base a, and then exponentiate that, you just end up right back at r. Right, so you haven't done anything. They undo each other. And they undo each other in the opposite direction as well, right? So what I mean by that is if I take r and I exponentiate it, so a to the base r, and then I take the log of it, that should undo it. That should undo this whole process. So indeed I end up right back at r. So they really are inverse processes. If you exponentiate something and then take the log of it, you've undone everything that you did. By the way, property number 7, you can think of this as following immediately from 3 and 4 together, right? What does 3 say? 3 says I can pull this exponent outside, so this becomes r times log to the base a of a. And what's log to the base a of a? Log to the base a of a is just 1. So this is r times 1, which is r. Awesome. So here's the properties of logs that you should know. If your variable here or your argument is equal to the base, then you always get 1. And if you're taking log of 1, you always get 0. So here's a really common type of question, just to demonstrate that you know how to work with logs. Let's say simplify this expression. Log to the base a of x squared over y cubed. So I want to simplify this. What am I going to do? I have log of a quotient, so what can I do with logs of quotients? I can write this as a difference of logs, so it will be log to the base a of the numerator minus log to the base a of the denominator, y cubed. And there's one more thing I can do here. These exponents can also come outside as constant multiples, right? So this 2 becomes 2 times log to the base a of x minus 3 times log to the base a of y. And that's about as far as I can go with this. Oh, by the way, I want to point out something. We can only, if you look back at our properties for logs, there are only properties for logs of products and quotients, right? If you have something like log to the base a of, say, x plus y, a log of a sum, there's nothing you can do with this, right? None of those properties have said anything about logs of sums. So really common mistakes is to try and break this apart somehow, but you can't do it. All right, a couple of things about notation. Sometimes you'll see this, log of x. What's missing? I don't have a base here, right? We've always written so far log to the base a of x. If the base is left off, it's usually understood to mean base 10. All right, so it's just log to the base 10 of x. In higher level mathematics, it doesn't always mean base 10, but as far as we're concerned, if the base is left off here, log with no base, it really means base 10. As I said, mathematicians are notoriously lazy, so instead of writing 10 all the time when it's quite often used, it'll just be left off. And this one, ln of x, ln represents something called the natural log. So again, it's a log function, but the base is that number e. Right? Remember e from last section, 2.712 something or other? Right, this irrational number, well, it's log to the base e. So this is quite often called the natural log. And I only gave you the graph of the log function for a bigger than 1, for bases bigger than 1, and the reason for that is because these are the two most common bases we'll ever see. E by far the most common, and e is bigger than 1. So let's do an example. New space. We'll solve a log equation. Log to the base x of 9/16 equals 2. Alright, so this would be called a log equation because it's an equation involving logs. And it's asking what base here makes this value, log to the base x of 9/16 equal to 2. It's an unusual equation. I don't think we'll ever see equations like this really as we go through calculus, but it's a completely valid equation. And the only way I'm going to solve this is I'm going to convert this to our exponential form, right? What does this mean? This means that x squared should equal 9/16. So x squared is 9/16. So what is x? Well, I can square root both sides, right? If x squared is 9/16, then x should be the square root of 9/16. What can I do with that? I can square root 9 on top and square root 16 down below separately. And this is nice because they're both perfect squares. So that is 3/4. Now you might say, hold on. You might say, hold on, Dane, you messed up here. If this is squared and I square root, I have to be careful. I really should take the plus or minus square root, right? And that would be true 99% of the time. But if I took the negative square root, I would have negative 3/4. And remember this base here, x, that base of a logarithm, that's not allowed to be negative, right? So I actually do only want the positive square root in this case, 3/4. So that's really all the theory. We need to do several examples now of how this stuff works. So let's solve another log equation. Log to the base 4 of x minus log to the base 4 of x plus 3 equals -1. Right, an equation involving logs. So the question is, what value of x makes this equation true, if any? So what do I want to do? The idea, the goal, is to eliminate the logs. Somehow I need to get rid of the logs. So how am I going to do that? Well, I want to combine these together for starters, right? I want a single log expression equal something. So let's do that. A log of a difference, a difference of logs becomes a log of a quotient. So here's my numerator, x over x plus 3. Notice, by the way, I'm only allowed to do that because these have the same base. If the bases were different, I couldn't combine them, but this is the better situation to be in. So what now? Well, now I want to get rid of the logs altogether, right? I'm trying to solve for x here. I want to isolate x, but it's stuck inside of a log. So how do I get rid of it? Well, I remember that what this really means is that 4 to the minus 1 is equal to x over x plus 3. 4 to the minus 1, by the way, let's not write it like that. 4 to the minus 1 is 1/4. So I want to solve for x, right? What value for x makes this equation true? How do I do this? At this point, I think some students might get stuck. What you tend to want to do is just clear this of fractions, right? So multiply both sides by x plus 3. So x is equal to 1/4 times x plus 3. And the reason I did that is because now I can distribute this. X is equal to 1/4 times x plus 3/4. And now I can group my x's together and isolate x. So anytime you're working with a fraction, something like this, where x is on the top and the bottom, you end up wanting to multiply or cross multiply. I probably should have multiplied both sides by 4 too, then I could have avoided these fractions. Yeah, we'll keep going with this. So anyway, subtract 1/4 x from both sides. I've got x minus 1/4 x is positive 3/4 x is equal to 3/4. I want to solve for x, multiply both sides by 4, divide both sides by 3, and you'll just get x is equal to 1. By the way, let's come back here and check this. Let's check that this actually worked. If I plug in x equals 1, what do I have? Log to the base 4 of 1 minus log to the base 4 of 1 plus 3 is 4. What does that equal? Log to the base 4, 1. Log to the base anything of 1 is 0, so that's 0 minus, here my base and argument the same, log to the base 4 of 4 is equal to 1. So indeed that is minus 1, which is the right hand side. So we checked that this actually works. X equals 1 is a solution. And according to us, the only solution. Alright, here's another one. ln of 5x plus 4 is equal to 2. Alright, well, just like the last equation, I want to isolate x, which means I need to get it outside of this logarithm. And how do I do that? Well, I remember that this means log to the base e. So this expression really means e squared is equal to the inside. So 5x plus 4 must equal e squared. And how about we do this all in one go here? This means x equals, subtract 4 from both sides, e squared minus 4. 5x equals e squared minus 4. We'll divide everything by 5. Not a particularly difficult example. The reason I did this was twofold. One, just to work with natural logs a little bit. Two, is to point out that this is the exact answer, right? This is what you would enter into MyMathLab, e squared minus 4 over 5. Don't plug this into a calculator and get a decimal approximation or anything. This is the exact answer. E squared is a number. It's a perfectly valid number, just like 4 and 5. So go with this exact answer. All right, here's an important example. This is not a log equation, right? It's actually an exponential equation. Exponential function equals an exponential function. In the last section, our goal here was to make the bases the same, because if the bases are the same, then you can say, you can equate the exponents, right? Unfortunately, no matter how you try here, you're not really going to make the bases the same. Right? We worked with like, okay, we recognize one base was a power of 2 and the other one was also a power of 2 or something like that. Here you're just not going to be able to do that, right? So instead, what I'm going to do is I'm going to take the log of both sides, right? If this number is equal to this number, then log of this number should equal log of this number. So I'm going to take log of both sides, and the log most people would choose here is the natural log. So I'm going to take natural log of the left-hand side equals the natural log of the right-hand side. Other good choices might be log to the base 2 or log to the base 3, but natural log's fine. Just go with natural log. All right. Why did I do this, and why is this such a powerful method for solving these exponential equations? Well, I want to isolate x, right? Eventually I want to isolate x, and this is such a powerful technique because now I can get x, which is stuck in the exponent. I can get it out by using our log properties that say that we can pull this outside, these exponents outside as a constant multiple, right? Well, I suppose it's a variable multiple in this case, but it's x plus 1 times log to the base 2. And over here, this is x times log to the base 3. This is invariably how you pretty much always solve these equations. Don't even go through that process of trying to make the bases equal anymore. Just take the log of both sides. If you're stuck with an x in the exponent, take the log to get it out of the exponent using this property. Now I just want to group all my x's together. I've got x times ln of 2 plus 1 times ln of 2 equals x times ln of 3. I'm going to group them all together on one side, so x ln of 2 minus x ln of 3 equals we'll bring this over, minus ln of 2. Okay, I've got ln of 2 x's and ln of 3 x's. We'll factor out the x. That's x times ln of 2 minus ln of 3 equals minus ln of 2. And now we'll just divide. So x is minus ln of 2 over ln of 2 minus ln of 3. Again, don't plug this into a calculator unless my math lab wants an approximation or something. Ln of 2 is a totally valid number, ln of 3 is a totally valid number. I don't have a nice decimal sort of value here to give me an idea of what that number actually is, but it is a completely valid number. This is the exact answer that you should go with. One thing you could do if you wanted to simplify this a little bit more, although some people might say this form looks a little better, ln of 2 minus ln of 3, remember I can write that as ln of 2 over 3. Is it prettier? I don't know. But either way, there's the answer. We'll do one more. We'll solve 5e to the 0.01x equals 9. Try this one on your own. Pause the video here. Try this. See how far you can get. But after you unpause, I will solve this. And the method should be very similar to last time, right? I want to get the x out of the exponent here, so I want to take natural log. Right? I want to take logs of both sides to get the x out of the exponent. And one thing I'll do to simplify what happens down the road, I think, is I'm going to divide by 5 first. So I'm going to write this as e to the 0.01x equals 9/5. You don't have to do this. I think it avoids me having to do some log algebra down the road. So now we'll take natural log of both sides. And again, this is why this is so powerful, because now using this property, I can get this x out of the exponent, right? This becomes 0.01x times ln of just e equals ln of 9/5. Well, remember, what is ln of e? ln of e is just 1, right? So that's really just multiplied by 1. I don't even need to write it anymore. And that means x is ln of 9/5 over 0.01. And there's my solution. By the way, if you want to make this look a little bit prettier, dividing by 0.01 is the same as multiplying by 100. So that would be 100 ln of 9/5. I will say one more very quick thing. I don't think it pops up in any of the homework questions, but it is nice to know. It's the so-called change of base formula. So I'll mention it very quickly. We won't do anything with it. Change of base is the following. So if I have log to the base a of x, I can change the base. So my base right now is a. I can make this log to the base b of x. But obviously I can't just freely change it, right? If I change the base, it should change the value. So if I change the base to log to the base b, I have to divide by log to the base b of the old base of a. Right, so if this ever proves useful to you, there's the famous change of base formula. Right, so very quickly, just something like log to the base 5 of 10. Maybe I want to change this to natural log, so I change the base to e. So that's ln of 10 divided by ln of the old base, 5. That is logarithms. It's one of these review topics that you're probably less familiar with than all the stuff we've reviewed so far. So make sure you're comfortable using these log properties because logarithms are a big deal throughout calculus. Thanks.